Judith, welcome to Specialist Tech Bytes. I really appreciate you talking to me. Like, one of the first questions I'm asking everybody in the season 1 of Tech Bytes is this is AWS Specialist Tech Bytes, and we want to showcase specialists at AWS and the work that they're doing. And the question I usually ask is, what would you say your specialty is, or do you specialize in at AWS?
So as a specialist, I worked mostly with AI ML and generative AI domain up until 2023, late 2023. And then I got interested in physical AI space as NVIDIA started publishing and promoting all the services that they have, right, with related to physical AI in the simulation environment and so on. And we also had all the services, but not put under the umbrella of physical AI from AWS, but it was distributed. So I was very interested in it because my background is as an electrical engineer, and I worked with robotics for a long time before I was a solutions architect. So these two domains, what I have had done in the past and what my role has been in the current scenario as a solutions architect combined, and I took interested in physical AI and thinking about how we can help our customers in this space from AWS side.
Yeah, that's always cool when your personal and your professional interests sort of align and you get to kind of pursue those things. And that was true for me when I came to AWS with IoT. Like I was always very curious in making things talk. In fact, the first book I ever bought on programmatic like IoT was a book called Making Things Talk. It was an O'Reilly published book. You know, I don't know if you're familiar with all those O'Reilly like how-to books. And it had little Arduino projects on how to get, how to use at the time. I think it was like 2012, like very early stage protocols for some of these things to get them to respond to you. And that was like kind of my first exposure to software development, was getting this little webcam I had on my computer to respond to a motion sensor that I bought from a place that no longer exists called Radio Shack. And then when it did that, it would send me emails. It was kind of like a Ring doorbell before Ring doorbell. And I think I did this back in like 2009. Maybe my timelines might be mixed up. I'm getting old now, but yeah, that was fun. And so like that was I had a very early interest in IoT, and then I started in my professional life, started getting exposure to IoT, kind of took interest and say, hey, I'll figure that out. I got exposure to Greengrass and AWS IoT services. And then now, don't do as much IoT now, almost all AI like you, but the physical AI seems like one of those really cool kind of like booming new spaces that could really bring me back. How did you first start like getting interested in physical AI? Was it something that you decided to do, or did just an opportunity came up?
Yeah, I attended the NVIDIA GTC 2023, and there were already some customers who were experimenting with natural language commands to the robot, right? Like they would say, go home, and the robot would go home. So so that was what got me interested in. And
Was that using an LLM? Were they using LLMs under the hood for that? Okay.
yep,
And
using
what'd you say? What year was that?
2023.
Okay, 2023. So like right at the cusp of like reasoning models, but
Yes.
not quite like, yeah.
Yeah, as we have now, like the humanoid robots and all the advancements that we have done we have seen in the last 3 years, it was very early on. And at that time, you can actually do these commands, give these commands, natural language commands, use the LLM to interpret and translate to robotic motions and actions, right? So it is very similar to how you would use a LLM to convert natural language commands to SQL and you query a database. So it is the same concept, but it has another layer added to it, a physical operation layer, where you're not just converting it from one data format to another. Now it is converting natural language to physical actions.
Yeah, this is where my head starts to like explode in the physical AI space, because like, yeah, so there's this kind of process by which we interpret natural language. So we're not like writing syntax or programming like move left, go up this many clicks, and then do that. Like, you're not programming that. You're actually saying, hey, I want you to go grab that thing over there, move it over, and you're naturally just talking. And then the LLM takes that language and reasons what you want to do, and then interprets that into the commands it needs to send to the robotic arm. But that's very basic. There's a lot more to it. I've learned recently, like, there's all this simulation training, world modeling that goes into it, because how do you then get the robot to learn and to become more optimal in its execution? There's a lot of cool stuff. But yeah, I think functionally it makes sense. So you just take natural language, convert that into the commands that the robot understands, and then send it to the robot. When we talk about robots, I think a lot of people think humanoid robots, because Optimus is of the world. But that's kind of what we're talking about. I mean, that is a domain within the physical AI. Robots have been around for a long time in the industrial world. I think the first thing I think of outside of humanoid robots is like car manufacturing. Like, cars have been made by some form of robot for a long time. Maybe when you think of robots, what kind of robots are we talking about?
So, like you mentioned, right, there's a wide range. So when it comes to humanoid robots, we see all these robots that can dance, and so those robots learn from human motions, right? So you teach the robot through imitation learning, and the robot tries to, and you are essentially training the robot model, just like you would do any other model, where you collect a data set of the motions and the robot continues to learn from it. But we are also talking about any entity that is smart enough and the hardware infrastructure to train and learn from what it has seen and to replicate the action and to adapt to new environments, so on. So in the manufacturing environment or automotive environment, we're talking about all these industrial robotic arms. It is essentially a bunch of servo motors put together, right? That they are programmed and they have these degrees of freedom, like how many joints, like our arm. So this is a joint, this is a joint. And how many, so this is a degree of freedom, right? Like I can rotate around that axis. And you are also right in the sense that they have been there for a long time. And when I said that I used to work as a robotics engineer, is essentially teaching the robots that come from different OEMs like Fanuc, KUKA, ABB, and teaching these robots on a particular action, right? Like and it is very straightforward machine programming. Go to this coordinate and then pick up the object. So whatever the end effector is, right? It could be a gripper or a vacuum cup or whatever. So it goes to that coordinates, picks it up, and then we would say, okay, drop it here. This is a pick and place operation. So it was all very programmed to the exact coordinates, and it would be saved as a program and as a system. So if the robot has to communicate with another robot or a conveyor or whatever the physical environment is, we do system integration, and they would talk through a PLC, the programmable logic controller.
Right.
So that's how we've always done it. But now, and it takes a while to teach these robots, right? Because any variation in the product, a very small variation in the product or the environment would cause a robot to fall, because we have these safety measurements like collision detection and so on. So it would take system integrators and the engineers a while to dial in and make these robots perform the motion without faulting out. So, and they would gradually increase the speed at which the robot, once they're comfortable. So we are talking about a few months to train a robot.
Yeah, it makes a lot of sense. I mean, I can imagine fault tolerances are pretty slim when you're I mean, how many things can trip up? It's funny when you were talking about pick and place, it kind of reminded me, sometimes I feel like I work on, my wife and I have this homestead, and sometimes we talk about doing farm chores and all these different tasks that we have to do. But like, sometimes I feel like 2/3 of the work that we do is just moving stuff from one pile to another. Like, that is like, if you boil down or abstract away like all of the things that, like feeding goats or feeding chicken. Like really, we're just taking this stuff and we're moving it over here. We're just making this pile go over to this pile, and it's just reorganization of piles. I feel like robotics is like same thing. Like how many use cases are really just pick and place use cases? You're just trying to get this thing picked up and moved over here. Whether that's like a package coming in off a delivery truck and a robot is trying to get it picked and placed into a bin, or moving a windshield from the bin to the car frame. It's like a lot of pick and place things. But that makes sense that you'd use some sort of like traditional ML modeling to get this thing moved. But LLMs are changing that, right? Like how are what's the help me understand the distinction between the traditional ML model approach and what LLMs are now allowing us to do.
Yeah, that's a great question. So there are like these traditional models that we do have specifically for robotic tasks, right? So there are many different models. One of them is this action chunking transformer model, and then we have diffusion model that are trained on a data set to perform a particular robotics task. Now,
wait, Judith, is this what we call VL? I think is it the term VLA models?
Yeah, it is built on top of it.
Okay, I heard that term. I mean, of course, I'm familiar with LLMs, and now I hear the term SLM a lot, small language models, not a lot, like within the context of fine tuning, but VLA is relatively new. I know nothing about how they're engineered or developed, but that's what you're talking about.
Yeah, these are the models that are one step above, right? Like you said, LLMs. How do we use LLMs? So we have these basic models, like for example, ACT model, like I told, that chunks the actions that the robot is supposed to do so that the motion is continuous and smooth. And now if you want to add different layers on top of it, right? So this is the base level motion. For example, it is like controlling our arms and legs to go to a particular point, but we don't randomly walk, right? Our brain is telling that, okay, I want to do this particular task, so I'm going to walk. But the underlying motion, our brain is already tuned to know how to perform that motion, how to reach that point by walking. So similar to that, there are these underlying models that are like action chunking and so on that tells how to perform the action. And on top of that, if you add natural language to it, so vision language action model, the one that you were talking about, is one such thing where you add the layer of giving natural language commands, and the vision is incorporated into it, and it also adds the layer of multitask reasoning. The model does, like the brain, the reasoning, the vision, and the ability to comprehend natural language. And then we have these underlying models that perform the actual motion.
It makes sense. So is it like is the distinction in the model development like, and maybe this is a really ignorant question. Like when we're talking about language, we're talking about creating vectors, which is a mathematical representation of the language, statistical likelihood that a word will come next in a graph, basically, right? We're talking about vectorizing text and then storing it in a vector space. And then when you're query, and then that's called that's the embedding. And then when you query against it, we're looking for those like statistical similarities to create. And there's all kinds it's much more complicated than that. I'm not a model engineer. I know there are all kinds of really smart people who come up with different architectures to make embeddings better and retrieving embeddings. But with but what you're saying with the VLA, it's still kind of fundamentally those principles, but with visual, but it understands, it's been trained on the visual element, like 3D model space, like how do we interpret the real world in a 3D like way? Is that like the right way to think about it?
Yeah. So these are multimodal models, right? Like for example, these are one step above the language reasoning models, like Nova Pro. These are multimodal where they are trained on multimodal data set. They can understand images, they can understand and do reasoning, and they can understand text. So it is a combination of these factors that they're trained on and made to integrate with other lower level models.
Okay. Okay, but yeah, that's cool. Like I wonder like it's always I'm just starting to feel like and like I'm really like there are patterns and frameworks that are emerging and just like in chatbots and RAG and text based you know those that dust I feel like is starting to settle. It like blew up for a couple of years and everybody was like there's like a new thing. I mean that's still the case. But I think some of the patterns are starting to emerge and stabilize. Is that happen? Is that still in the physical AI? Is it still like blowing up? Because I feel like I asked that question because like one of the things I'm in deep right now are model evaluations, not just in the model itself, like accuracy and but in like retrieval, like RAG systems, like how do we start to evaluate how well it's effectively
Mhm.
it's retrieving
Proxy process.
information? Yeah, and then I'm talking, and then the output, like what does the model actually like based on your system prompt and based on your context that you've developed, is it producing? How deterministic are we? Is it producing the output you want? So we can sort of start baseline and we can say, hey, this model is doing what I wanted to do, or this agent is doing what I wanted to do. And here's the baseline. Here's how it's getting better. That's like, I see that in the evaluation space. And I'm like, how much of this stuff is translatable to the physical AI space?
That's a great question. Even for agentic evaluations, right? We talk about how do we evaluate the agent actions. So if you see, so zero-shot prompting, we had the models with zero-shot prompting. We ask a question and it's done. And then we evaluate the response, right? And then there is agents that still perform the actions in the digital world with tools. And then how do you, so it would be similar to that of an agent performing a task and evaluating all the actions that the agent has taken, but now you're translating it to the physical world. So it would be,
Yeah, makes sense.
yeah, the but yeah, the LLM as a judge evaluation model is what you would do, but you'd use a VLA as a judge evaluation model.
Yeah, I mean, I guess that makes sense. Like you're still, yeah. I think maybe it's easier for me to cross the bridge from like agent evaluations because there's some action that results. It's not just a text coming back. That's maybe a simplified like that's our OG chatbot, which is essentially like glorified Googling. Like it just sounds a little more human than just a list of results. But agentic, like when we get into agentic space, okay, now something is being done, something's being orchestrated, and we have to evaluate that action. Is it the action that we intended? And that makes a lot of sense. That makes sense to translate that to the physical AI world. Like, did the robot
Complete.
or yeah, did it complete, and how well did it complete, and how many steps did it take? I can imagine where like as it gets more efficient, I'm thinking about this in the agent space. Like we want efficient tool calling. We don't want the agent to have to like figure out and reason every time it gets asked to do something. So
Exactly.
there's this idea of optimization over time where the agent's like, hey, I've done that before, right? It has memory. And it's like, and I can do it a little bit better if I just tweak it like this, and it gets slowly optimized. I can see that totally translating to the physical
Mhm.
AI space.
Yeah, and you're
Uh,
adding parameters, right? Like throughput, latency. Latency is very important. So unlike where we have agents going and doing whatever they want to do, the task they are assigned to do, and we are patiently waiting. But in the physical world, when the robot is performing a task, especially in a high-speed environment like manufacturing or automotive, so that these are the parameters we take into the evaluation as well. Like what was the throughput? What percentage of the task was completed in a given amount of time? What was the latency? And so on.
Yeah, yeah. And so when you're running these evaluations, I imagine, and this is maybe what we can dive into because I know you've done some work in this space. Like doing that sort of evaluation with an actual robot. One, you don't always have an actual robot. Maybe they're really expensive sometimes, and maybe somebody else is using it, or you don't want to use your production robot to. So there's some sort of like simulated training that you want to do in a modeled world instead of the real world because doesn't always make sense to do it in the actual world. You don't want the robot making mistakes in the real world. That could be anywhere from something like really dumb and it just takes longer, or it could be really expensive. It breaks something or hurts something. So we simulate that, like that, and then you run those evaluations in the simulation. What's the challenge with that? Like when I think of like 3D simulated world, I think of just like video games. Like we've become how far video games have come and 3D world building has come. But I know that's a huge space in physical AI. It's like modeling the real world and being not just kind of like the real world, but like the high degree of fidelity like the real world. In fact, isn't this is Elon Musk's evidence for simulation? Like, look at how advanced we've gone from early ping pong, like Pong game graphics, to like world building graphics today. But we're leveraging that kind of simulated environment, I imagine.
Mm-hmm. Yeah, yeah. So the simulation environment helps us, at least how we've been approaching it with our technical assets, right, is to mostly collect data, so that when we have the model running at edge, the robot very closely aligns with what was done in the simulation environment, uh, and able to perform the task regardless of how all the variabilities, right? The environment or the parts that it has to manipulate. So and there are different use cases as well. For example, like I said, latency, how fast the robot controls completes the motion and accurately is one parameter. And in some use cases, the speed does not matter, but the precision at which it completes the task matters. So I can, if it is a high speed task, I can get away with, for example, 85% accuracy on if it meets the success threshold, and I set it as 85%, I'm okay with it. So as long as for a pick and place, I'm not wanting to place the object in the exact same spot. It can be in this target area, right?
Yeah, just get it in the bucket. Yeah,
Get it in the bucket. So at
yeah.
that point, I'm happy with 85%. That is the threshold I set. And if it meets that accuracy, I'm okay. But in specific use cases, like for example, in health sciences, like surgery, where it is, you have to be very careful, like half a millimeter matters. In that case, I'm not really concerned about how fast I do an operation, but how precise I meet
Yeah.
the success threshold, which I would set up at 99% or above. So in the simulation environment, like you said, the robot can only function well and achieve the results based on how well it was trained. The model was trained, right? Like in the simulation environment, or even while teaching the robot, just like any other model, we want to give it a diverse data set so it is not biased, or if it is shown on a new environment or new variables, it just doesn't know what to do. So we want a diverse data set. So one approach that we had taken with the assets we develop is we teach the robot with as much diversity and new environments as possible. So it learns from these diverse data sets. And we also generate synthetic data from these diverse data sets. So we are not going to spend like a GPU time or GPU resource to manually show every single possibility to the robot, but we are able to project different environments from what the data that we have gathered, so that we have that data as well that the robot is.
Yeah, that's interesting. Like in the synthetic data generation, I imagine becomes like I've been reading and hearing about like how we've just run out of data. So like it is inevitably synthetic data that we will have to create in order to get better, make that next step, which is like bonkers to even think about how much data we've already just burned through in such a short amount of time to train these things. But like, okay, but I hear what you're saying. Like within the synthetic data creation, we want to have enough variability that the robot is learning new and managing cases, but there's got to be enough correlation in the data to achieve some outcome. If it's too random, it just doesn't ever really learn a pattern and do the right thing. I think the medical use case is really fascinating. Like more and more surgeries are being done by robots or robot assisted. I can see a world where like these models help assist even more. I mean, not careful not to say fully automated, because there might be some uncanny valley. I don't know if that's the right term, but that we'll have to cross to be fully trust a robot and a VLA to do surgery on you. But that's where that precision comes in. And you want that robot to have experience enough variability because it may encounter things within the context of that surgery that it has to deal with, right?
Mm-hmm.
Because people are complex and unique, and you don't know until you cut open and you get in there, and
Mm-hmm.
that's fascinating. The synthetic data model generation is going to be a really, really interesting world to explore, especially as it
Mm-hmm.
pertains to like these different models and what they're capable of doing. And how do we, what's the right balance between constraint and variability to keep getting better?
Mm-hmm.
Man, that's interesting. And
Yeah.
that's going to be so true in physical AI. Okay, so you use this simulated world to create synthetic data because we want to train the robot more efficiently.
Mm-hmm.
And you said you seed that with some real world data, and then you infer from that real world seed data some synthetically generated data, and then the model can kind of chew through that to get better.
Mm-hmm.
Is
That's
that the right way to think about it?
Yep. Yep. So one example is you teach your toddler how to behave, like at a party. You tell, like, this is not your party. You have to share toys. And you prepare your toddler for the real world. And then you go to the party, and then something happens, right? And you're seeing a new situation, like another kid, acted aggressively to your kid. Now the kid was not trained on how to behave in that environment, right?
Yeah.
So you take that data point and you go back. You do as much damage control as you can when this is happening in real time. But you take that as a data point and go back and talk to your toddler and give examples of how that can be handled in the future. So it is similar to that. You can
So
train
you're the human in the loop as the parent.
human in the loop as the parent. Yeah.
Right.
So
I
you
love this. This is a good analogy. I heard somebody recently describe small children as fine tuning in LLMs, that they're just little LLMs learning how to interpret context of the world. So that's what you're saying. That's a perfect analogy. Well, I wouldn't say perfect. I hate to think of my 2-year-old as try to give them a little bit more value than some GPU somewhere.
Yeah, we're more than that, or at least we would like to think so. But
Yeah.
but it is the situation is similar, right? Like if you narrow it down to what we are seeing. So when we do simulation to real and we deploy the model and the robot is performing, there may be some, and we want to track it in real time, right? So we have this telemetry data from sensors, from vision models that actively tell us what the delta is between what the model was trained on in the simulation environment to what we're seeing in the real world. And then we have this calibration workflow. So that is similar to teaching the toddler how to perform the next time the toddler sees something like this in the real world. So we take the data points from the sensors, cameras, all these data sources, and we train the model again or fine tune it, more like how to handle that particular exception. So this is a closed loop feedback system that we have the model continuously train on. And the beauty of the AWS system is where we try to scale it. So AWS services are highly scalable in the sense we have these IoTs, IoT jobs, IoT green grass, and for fleet management and device management, meaning that so I'm collecting all this individual data from the robots in the field. So these can be any robot, right? It can be humanoid robot. It can be a stationary robot performing a task. So we are continuously getting the data from each robot, and it need not be an isolated system. So one robot sends the information, and we know what we need to do based on the data, how to fine tune it, and we extend that learning to other robots as well. So it is like a fleet management that we have there. So we have like real world agents out there that collect data.
Oh yeah, that makes a lot of sense. That you would essentially federate data collection to not just the one robot but like all of the robots. Use that as a mechanism to train the next fleet or the next update, next patch to your robot or model that they're using. I can like, man, the architectures that, as a solutions architect, just as a builder generally, as you described those things, I'm like, man, how would I build that? And how would I do that? And what are and I imagine IoT, AWS IoT services are, are, are the backbone of enabling those things, like getting that data collection at the edge primarily, really, and then sending it back down to the edge to be used. Are people using, model distillation for VLAs to get inference at the edge as well? Like, is that it? I know that's got to be a thing. I'm sure it's a thing.
It is. And we use mostly SageMaker for that, right? So whatever distillation or model optimization we need to do, like you mentioned for inference, we use SageMaker for it.
Yeah, it makes sense. You do the fine tuning and the heavy lifting of model in the cloud, and then push the smaller, like kind of distilled, finely tuned, whatever you want to call it, a model out to the edge so it can actually run on the hardware that exists on the edge. I've been really thinking, this is really fascinating to me, because one of the things I've been writing a paper at Amazon. There's a doc writing culture, and I've really loved that because I have these ideas, I have these inspiration, and they're kind of fleeting sometimes. And I'm like, I'm going to forget this unless I write it down. And I was just talking to somebody on this show recently. In one of our episodes, we were talking about, hey, now we can kind of talk to an LLM and not let that fleeting thought be lost to time, or we can kind of just speak. He said he talks to his LLM on the way to work, and that's how he captures some of his ideas, and then he can model them from there. Anyways, one of those ideas for me was like this localized inference. So I have to imagine that, like, as computational, two things I think are happening right now. One is the computational capacity of our local machines is increasing. That's obvious. If you look at like the NVIDIA released the Spark, which is like a local, they're calling it their AI computer. Apple has a Mac Studio. It's got integrated memory. It can run inference models, smaller parameterized models. But then you look at these other, like, there's all these things happening to get models to run on localized hardware, which is to me a very similar thing as like edge inference. Like I need this inference to occur. I don't need a GPU. I don't want a GPU. I only have a CPU. How do I get this to run on a CPU? How do I quantize down to something my memory can handle? Like I can load this into memory. And then how do I distill and fine tune it so that it's like actually functional and work on these smaller versions of these models? And I think as far as like AWS is concerned, I've been really thinking about like, how does that impact cloud development? If it's true that we're going to be like more increasingly dependent, it's going to increasingly become cost efficient to run models locally, and I'm not going to rely on these massive GPUs and some specialized hardware that only AWS exposes. But what's the opportunity? Like, what is the thing that actually needs to be done? And I think you're alluding to it a little bit with IoT. In Greengrass, it's the control plane. Not everything is going to be able to occur locally. You're going to still need that horsepower in some ways, but then how do you orchestrate either the data that trains it to get better or push the model back down to get? There needs to be this still centralized kind of mechanism to enable even the local version, because we want to make these things better and tuned. And I don't know. I'm kind of like rambling now, but I've been thinking a lot about that, especially as I save up my pennies for a Mac Studio that has 700 plus gigabytes of integrated memory, which is like thousands of dollars.
Yeah. And you're right? The compute at edge and the compute at cloud is important, as well as the data lake in between, where we use the data and curate the data so that we can keep this loop going on. Yep.
Yeah, that's a really important piece of the data, not just the control plane, but the data plane as well. Like, and that's something that AWS is, I think, you're getting better and better, I mean, at doing, which is enabling all of these data tools, data storage, really cheap data storage, query access, data sharing, data permissions, data security. Yeah, that's a really important part of it. Not to sound too much like a commercial for AWS, that's not the point of the show. we do work for the company, and we're biased. But it's just fun. It's just like cool to work on these, like solve these problems. Like, you know what? There's this like fear. You know, sometimes we talk about AI. There's a lot of people that like you hear a lot of anxiety out in the world around people like it's going to take over our jobs. It's going to do all this stuff. And I think, you know, I don't mean to diminish that. I think there's some basis of truth that people should be concerned. We should be having these conversations. We shouldn't ignore them. But there's also still so much to build, and there's still so many opportunities. And I keep telling people like, you know, I've had some younger people on our team say like, hey, what advice do you have? I'm just getting started in my career. There's all this stuff. And I'm like, oh man, I've never been more excited to build at AWS than I am now. There's so many opportunities and things to explore and different dimensions to go down this rabbit hole. Even what we were just talking about in local, you know, inference at the edge and how do we enable that, or physical AI and how do we enable that? I don't know. That's just my 2 cents on the whole anxiety that people are.
Yeah.
But Judith, you said you keep referring to something that you built. People can actually play around with some of this stuff in a simulated environment. They don't have to have a really expensive robot at home.
Yeah.
How do they do that? Like, what do you got? Like, maybe you can show us what you've been working on.
Sure. So let me share the screen. So I believe you can see the robot moving, right? So this is a UR5 robot, the Universal Robotic Arm. So I zoomed out to show how the robot looks like. It is a stationary robot, and so the task for this robot, so it has two cameras, one overhead, one on the wrist of the robot. The task for this robot is to push that red T object on the target area. So we begin by teaching the robot like a few of the human demonstrations with the PS4 controller. So we start the simulation, and then this is the Isaac Sim environment, by the way. So Isaac Sim provides different robots that you can real robots that are there in the real world. You can pull their digital twin, for example, and put them in the simulation environment, and then you can add objects and the environments in Omniverse. And so this is what we taught the robot on, right? Like very few demonstrations of how to move. So it's like a gaming thing, right? You move the arm, and you like a teach pendant, and you teach the task. And then with imitation learning, we have written a script so that it continues to collect the data set that it wants to be trained on. The model can be trained on at a later date. So I will show you the live view of the script, and here it is. So I'm just I'm not doing any fine tuning or training right now. I'm just collecting data.
Okay.
So this is the episode data that, and you can see all the steps. So we have like the cameras, observations, the images that it collects, like 10 frames, and then it sends to Nova Pro. And Nova Pro acts like a coach, where it sees what's happening in the simulation environment, and it acts like a coach. It tells, oh, the robot is moving very slowly at this point. We can increase the velocity a little bit more. And it would be a better approach for the robot to move from this side of the bar and push it first. So it it accomplishes the task faster. So we collect all this data, and here you can see the accuracy, right? 61%, 60%. And once it reaches the threshold, like I said, I set it as, I think, 85%. It would say, okay, I have enough data for one episode. Episode is like from the start of when the robot moves from the home position to the end of the successful completion of the task. So that is an episode data.
When you say
And
accuracy, you mean how much of that T-bar is within the outline that you give it? So you said 60% is like, it's only 60% of that red is inside of that outline, but you're saying the goal would be, we want to be more accurate than that. We want to be more precise than that. Let's get it to 85%. And then Nova is interpreting the visual aspects of that in addition to the data of the actual arm, its location, and on that, and it's coaching the arm or the mechanism that's controlling the arm to say, hey, try this, do that. And okay.
Yeah, exactly. So, like you said, accuracy is how much of the T-bar overlaps over the target area. And we are using a action chunking transformer model. We are not using VLA over here. So right now, what you're seeing is it went past um, the recording went past when the T-bar was overlapping 85% of the area, but it captured that data, right? It stopped right there. And then now it is recording all the data in Parquet format. And it is recording the video as well. The video of it starting to record the data and then doing all the actions based on like the input images and the observations. And it records all the data. And I have this data set in Parquet format. So I think right now I have many episodes saved. The goal is to have a lot of episodes saved so that I can take this data set and train the robot model on that data set.
Oh, I see. That makes sense. So like you're saying, hey, our goal is to get 85% accurate. As soon as you hit that stop, take all the data that you collected to get to that point. That's an episode. And then you're saying, let's collect enough episodes that of how we achieved 85%. And then we'll take that collectively and we'll say, okay, model, here's how we did this. We did it kind of slow and chunky, and it took us we took some left turns when we maybe should have taken some right turns. But go learn from these episodes so that the next time you attempt again to interpret what you're seeing, you're much more efficient, and you can get an episode time gets shorter. It takes less time to go from the home position to 85% because it's learned.
Yeah. Yep. And we use a hybrid learning method here. So we initially, like I said, taught the robot on the data that we had collected with human demonstrations, and we also add the reinforcement learning component to it. It is a very basic reward-based reinforcement learning system where it gives itself rewards the more it takes it closer to completing the task. So every motion of the robot, right? And it gives itself penalties when it takes it away from the task, when it loses accuracy. And we keep fine-tuning it that way with the reinforcement learning and continue to collect data from it. So the model gets better and better at getting this data at a faster rate.
Yeah. I mean, back not to belabor our toddler analogy, but you can imagine it's like, hey, watch me first. I'm teaching my son how to play golf right now. He's actually amazingly good for a 2-year-old. I know every dad says that, but it's like, hey, watch me first, dude. Like, we're going to hit this ball. This is how you do it. And then he learns it. Now, I haven't, we only do positive reinforcement at our house. I haven't started punishing him yet for not doing what I want him to, at least not in golf. But like, I can see like eventually he starts to learn from that. And in the same way, like we said, toddlers are little LLMs. The same way this is doing something similar. That's cool. And that people can use this, right? Like we have this published, and if they wanted to spin up their own Isaac Sim environment and follow the same patterns you did, that's available.
Yep, there is. Let me share this part of it.
And what they get with like this thing is like what you've just described is not just like the tooling that you need, Isaac Sim, and it has all of these different robots available to you, but it's also the process, like the the framework that you kind of followed to achieve this learning optimization loop that you've developed. And so if you wanted to, you don't have to do the T-bar in a thing. If you have some other robot and you want to sort of recreate this optimization loop, you could use something like what you're showing now.
Yes. Yes. Well, I would say the easiest way to do this, and we are doing it right now with some of the projects we have, is so this is a USD scene, right? For example, um, universal scene description is where all the objects that you want in the simulation environment are there. So the robot, the T-bar, the table, the target area. So you can create your own USD file, um, create a stage and put all the components in it, and add physics to it so that the objects can move. Then for your use case, say if it was pick and place, then you would have the gripper scene pulled, right? Um, and then you can essentially use the same methodology. You can change the script with Kiro to now it is no longer T-bar, T-slot task, right? So you will define what accuracy is. You will teach the robot on that particular task in the simulation environment, and then you collect the data, and then but the underlying methodology remains the same. So you modify the components to make it for that particular task, and the programming for that particular task. Um, but yeah, the underlying script
Approach.
is the same.
Yeah.
Yeah, approach
I
same.
like what you said with the Kira. I like that's a hot tip. Like tag this. Like if you take this code that you've developed and use Kiro or Kiro CLI to understand the high level methodology, but adjust it to give it the the adjustments you want for your use case, and then it can modify just the details, not the overall approach. And then effectively you're creating your own simulation learning environment based on your requirements. We should write that up in a little blog or a little builder center thing. Like, hey, here's how you use Kiro to tweak this environment. I think that'd be really helpful. To break that down a little bit more in a tutorial. That's a good idea.
Yep. And also, I think Ben is working on this synthetic data, right? He has a LiDAR, and then he gets the scene that you can essentially take the capture all the details in an environment and then bring it to the simulation environment, and then you can essentially create data out of it and also generate synthetic data. Um, I am looking forward to incorporating that with this guidance. But I think that would be a nice talk as well to have with
Oh,
Ben.
so there's more work planned for this thing here. We have another person in the specialist organization who's working on a different aspect of this that we should maybe bring on the show and talk to. That's yeah, I've definitely, he's in my sights. I haven't had a chance to pin him down yet, but yeah, I would love to talk to him. Cool. Hey, yeah, I'll check it out. Hey, Judith, I think this has been a really good conversation, and I think this is a really good place to maybe wind it down. We've talked for a good amount of time, and that's a really cool demo. There's some things for people to go check out. I kind of just want to ask you, like, real quickly, like, what are you excited about most in the world of physical AI and the work that you're doing as a specialist, like coming up? Like, what do you look forward to?
Um, it is very dynamic and it changes. Um, I'm pretty sure when I come back from maternity leave in like 3 months, this will be obsolete. Like there will be new models, new methodologies. It is growing very fast, and all these BLA models, like you had mentioned, right? There are some open source ones, and there is Groot model, there is Pi Zero. They are continuing to make them better. And I'm excited about how fast it changes and how much there is to learn. You can never say like, oh, I found a way to solve this problem and then let it go, because it won't be true in a week or two, because it is evolving that fast.
Yeah, that's true. And maybe congratulations, by the way, on maternity leave, stepping away from that and coming back and seeing the evolution of that is something. What you'll have to do, I guess, we'll have to do is turn on the Judith LLM, and so it can learn and on your behalf, and then when you get back, you'll download its learnings. Hey, Judith, hey, thanks for talking to me. This has been really cool. This is like a really cool space. I know I'm going to have a lot of conversations in the episodes to come about physical AI. I know that's becoming much more of a focus for not just our team, but our organization and the company. Really, I mean, it's kind of the next frontier is taking these really cool reasoning and model in the world of generative AI and bringing it to the real world. So that scares some people, but it excites me.
Thank you. Yeah, it was really nice talking to you.
Hey everybody, thanks for watching, and a very special thanks to our guests for joining. Hey, if you want to stay in the know on what specialists at AWS are doing, make sure you grab a Builder ID if you haven't already, and join our space on Builder Center, where we'll be posting almost all of our content exclusively. We'll also have show announcements on X, LinkedIn, and YouTube, and we'd love to hear what you think and what you're working on. Until then, I'm Farmer Todd, and I'll see you out in the field.